Hello, everyone. This is the part where I welcome everyone who's watching it later. I'm going to do this discussion. Anjali's lab was canceled this week, so I'm going to record mine instead. Yeah, I don't know how Anjali does it, so I'm just going to do it the way I do it, and you can take it or leave it if you like it. So I'm going to begin treating this first question as a warm-up. I hope all of you are familiar with quicksort and know how to do quicksort. I'm just going to give you like a minute or two to do this. And if you don't know how to do quicksort, I'll just go over it at the end. So I'll just give you like 2 minutes as a warm-up. Sounds good. Okay, I know that definitely wasn't 2 minutes, but how do people feel about this? Should we just do this? Do people feel confident with quicksort? I didn't teach discussion last week, but I believe it was on the last discussion, right?
Yeah.
Kind
Yes.
of. Okay. I'm just going to do this problem quickly then, and because we don't need to spend a bunch of time doing it. I'm hoping you understand quicksort. If not, I would just review the slides and use this as an example. So here's basically what we're doing, right? The whole idea of quicksort is we are partitioning things into 3 arrays. We are taking a pivot and we're saying things that are less than the pivot, equal than the pivot, and greater than the pivot, right? And so I'll use the kind of 3-scan method, I believe it's called, that was in lecture. So this one is saying we just want to choose the first element as our pivot, which is a really common strategy. So in this case, 18 is our pivot. So all we're going to do is we're just going to go through the list left to right and just pick out every element in order that's less than 18 first. So we're going to go just kind of left to right. I see, okay, 7, that's less than 18. I see 11, less than 18. 4, that's less than 18, right? Then we do every element that's equal to 18. So that's 18 itself, which I'll mark with this underline because this is the pivot. And then there's another 18. And then I'm going to do everything that's greater than 18. So left to right, that's 22. That's 34, that's 99, right? So we have these kind of 3 subsections. Whoops, that is not how you draw. These 3 subsections, and that's like the first iteration. I hope that makes sense to people generally. And notice what quicksort does is it doesn't necessarily sort everything in one go, but it gets everything closer to where it should be. Yeah, so notice that this left array, leftmost array is not sorted yet, but the real position of 4 is here, the real position of 7 will be here, and the real position of 11 will be here. It's in the right place, right? Everything will be sorted within its subarray, so we can split this up recursively, I hope. Notice also that coincidentally this array is just sorted, but whatever. Okay, so our next, I'll just get rid of the boxes. So our next iteration, we're going to break these two, we're going to do quicksort again on these 2 subarrays. So let's do the left one first. We're going to choose 7 as our pivot. So same thing, everything that's less than 7, which is 4, everything that's equal to 7, which is just a pivot, everything greater than 7, that's 11. Notice also that these subarrays are all now length 1, and a length 1 subarray by definition is sorted, right? Because if you only have one item, it's sorted. So we're done with this side, we don't need to recurse anymore. I erased that. 18 and 18, we don't need to recurse anymore because if they're equal, there's no more way to sort them, so you don't need to worry about recursing on like the middle array. And then the big array we're going to recurse on. So we're going to choose 22 as our pivot. Everything less than 22, there's nothing less than 22. Everything that is 22, everything that's greater than 22. Notice also that like even though this is already sorted, quicksort doesn't like know it's sorted yet. All it knows is that everything on the right is going to be in that array. Yeah. So then we end up with like this subarray, which is the right subarray. We have this kind of like null empty subarray on the left, basically. And then we have the equal elements. So we do one more iteration of this, choosing 34 as our pivot. We choose everything less than 34, there's nothing. Everything that is 34 is just that. Everything that's bigger is 99. And now this is a subarray of size 1, so we're done. And now basically you combine all these subarrays again. So we just have 4, 7, 11. See these 18s from up here because they never had to be sorted. They basically just come down 22, 22, 34, 99. That's a really awful looking 9. Okay, that was a super quick sort, but that's like the basic idea of it. Does that kind of make sense?
Yeah.
Yeah.
Great. Okay, so I hope that's just kind of like a run-of-the-mill reflection question. The next thing is talking about quicksort with Hoare partitioning. Do people understand Hoare partitioning? That's what I expected. I didn't either because they didn't teach it when I took the class. So I will just go over it because I feel like whatever. We'll just learn the algorithm right now, okay? It's a mind-blowing algorithm right here. Okay, so here's what you do basically. I'll just write the steps down, and if you want to like copy them, feel free to copy them. Don't worry about the actual problem yet. We're just going to learn how to Hoare partition something first. So step 1 is you pick a pivot. I'll just call it P, just as before. And you can choose the leftmost, you can choose the median, you can choose whatever you want, right? You just pick a pivot. The next thing is you have 2 pointers. And in the lecture, Hug calls them L and G for less than and greater than. And then what you do, this is going to be really abstract, but I'll do an example so it'll make more sense. Basically, what you do is you, also these are at ends of the array. Then what you do is you basically move L up if good element, and then once it finds a bad element, you move G up if good element. Then once you have 2 bad elements, swap elements, and you move L and G up. And then you repeat this, and then you repeat these steps until you're done. What does that mean? Because that's really weird and abstract. Let's just do it on an example. So let me just write down the example from the first part, and we'll sort that by Hoare partitioning. So 18, 17, 22, 34, 99, 18, 11, 4. Okay, so what we're going to do is we're going to pick a pivot P. I'm just going to say leftmost is going to be the pivot again, right? So 18 is our pivot. And now we have this L pointer and this G pointer. So the L pointer stands for less than. The L pointer likes elements that are less than P. Not less than or equal to, but strictly less than. And it doesn't like elements that are greater than or equal to P, right? So for example, does P like 7? Or does L like 7?
Yes.
It does like 7 because 7 is less than P, which is 18 currently, right? G is the opposite. G likes big elements, right? So G likes elements that are strictly greater than P. And it hates elements that are equal than or less to. So G by default here is placed to 4. So does G like 4?
No.
It does not. So I'll just kind of run through this process a little bit. So we have this L. We're going to say, okay, we move L up if good, which I mean, by that I mean if it likes the element. So it does like 7, right? So we're going to move it up to 22. L does not like 22 because 22 is bigger than 18, right? So we kind of basically we scan left to right until we find the first element that is equal to or greater than P. Once we do that, now we look at G and we say, okay, G, does G like 4? It doesn't. So we're not even going to scan. We would be scanning, right to left, but we're not even going to do that because we already found an element we don't like. Does that make sense so far? I hope it does. Yes, someone said yes, great. So then what we're going to do is we're going to, once we have 2 elements we don't like, we're just going to swap them, right? Because if G does not like an element, L probably is going to like that element, unless it's equal to, which we're going to ignore that case for now. And if L likes an element, if L does not like an element, G is going to like it, right? Because of the way we define these things. So we just swap these 2, 4, and the other one was 22. And then we move both pointers up. So L goes up 1 and G goes, I guess, down 1. They get closer. And then we just keep repeating this process. So I'll just do a couple more runs of this. L does not like 34 because 34 is really big. G does not like 11 because it's smaller than 18. So we actually have another situation where we're just going to swap 11 and 34. And then L goes here and G goes here. And then we have this case, G does not like 18, remember, because we don't like anything that's equal to, we want it to be strictly greater than for G. L does not like 99, because 99 is too big, so we're going to swap these again. 18, 99, and we're going to move both of these up. So G is now here, L is now here. This is where we get to the next part, basically, which is once L and G cross, we swap G with the pivot, and then we're done with one iteration of this. So G is going to swap with the pivot. In this case, it doesn't matter because the pivot and G are the same, but we're going to swap basically 18 with 18, and then we have our kind of like subarray structure, and then we can just keep doing this. So some kind of insights on this. It sounds really weird. It sounds really convoluted, and it is. But the kind of big insight is that the kind of keep in mind what I was saying quicksort does up in this first example, let's scroll up, is it doesn't necessarily sort everything in one go, right? But what it does do is it gets everything closer, right? No elements will be farther from the position they should be after run of quicksort. They may not necessarily be closer, but they certainly won't be farther, right? And this is doing the same thing because notice the first, I'll scroll back in a second. Yeah, notice the first thing we did, the first thing we swapped was what, 4 and 22 or something like that, if I remember correctly. And 4 was over in the right section, and 22 was over in the left section. And you just kind of look at this array. Well, of course, 22 is going to be in the latter part of the array, and 4 is going to be in the earlier part of the array. So that's kind of the logic that we're trying to get things closer to where they should be, basically. And in that sense, it's basically the same as the other quicksort. Okay, so I kind of blew through that. Does that make any sense to people? Okay, I hope it does. Okay, pretty good. Okay, I'll take that. Yeah, the example in lecture I think given about this wasn't great. Honestly, I'd recommend looking up like a YouTube video and watching them do it or something. That's how I did it this morning when I was learning how to do this. Okay, but anyway, we'll get back to the actual like worksheet portion. So what is the best and worst case running time of quicksort with Hoare partitioning and n elements? And just because this is confusing, this doesn't actually change anything. If it's Hoare partitioning or it's the 3-scan method, it's going to be the same kind of case with best and worst. So if you have intuition for that, feel free to use that. And then, of course, come up with an example that will give you the best and the worst. Low-key stumped. Is anyone else low-key stumped? We can talk about some hints for this basically. Oh, okay. Well, apparently you're wrong for being stumped. But basically I'll basically say, like, do people know what the worst case and best cases are for quicksort? Not what the examples are, but just what the cases are, because I feel like these are things that you just kind of hear and memorize a lot. What's the best case for quicksort? Does anyone just know off the top of their head? It is n log n. Yeah, and what's the worst case? Yeah, it's n squared. Okay, so my question to you is then, like, what gives us these cases, right? So log n, we know in general in sorting algorithms and trees usually comes from like splitting things in half, right? Like that's how we get log runtimes. That's why binary search takes log n and linear search takes n. So using that kind of logic, when do we get a really good quicksort? Yeah. Oh, no one said that. Sorry, yeah, sorry if you were going to say the same thing. But yeah, so it's where we split things in half every time. And if you look up at this first example we had, once it scrolls up again, this is actually an example of quicksort working like pretty optimally. Because notice we split into a subarray of 3 and 3 on this side, right? Below that, it's not optimal because here we split into an array of 1 and 1. We split the 3 into like 3 things, but here it takes us more steps. So this is the kind of suboptimal, and this is the optimal, kind of encapsulated within one example. In other words, the optimal is when you're going to get like the median element so that you kind of split things, right? Because we're saying less than, greater than. So if we have the median element, it will be 50-50. If that makes sense, right? So if you were to just use the numbers 1, 2, 3, 4, 5, right? Where would you get like which of those would you want to use as a pivot? One, 2, 3, 4, 5 would be the worst case, sorry. But let's say that you have, well, sorry, I spoiled it. But yeah, let's say you can choose any of these as a pivot. Which one's the best one to choose?
3.
It is 3. So let's just do an example where the order of the other elements doesn't actually matter. But let's just say we use this, right? So what's going to happen? Let's say that we have our list and it's sorted 3, 2, 1, 5, 4, or it's not sorted and we need to sort it. If we choose 3 as the pivot, we're going to split things evenly because it's going to go 2 here, 1 here, 3, 5, 4, right? With 3 in the middle. And then these are kind of trivial. These are just size 2 problems. But you know, if we take 2 as our pivot and put everything on the left, we're going to get 1 and then 2 and then nothing. And same thing with 5. We're going to get 4 and then 5. So we do it like that. And you can imagine if you had an example where it was like size 7, for example, you would split into 3s and then you would split those 3s into kind of all 3s like that. So if you get the medium every time, that's the optimal way to do it. And then someone earlier said what the worst case is, and so I kind of spoiled it, but the worst case is when it's already sorted. Why is this the worst case though?
Because it keeps on splitting at the beginning.
Yeah. So yeah, because if you do 1, you're going to do everything that's less than 1, which is nothing. Then 1, then everything greater than 1. We've only really sorted one element, right? We've only, obviously this list is already sorted, but the algorithm doesn't know that, right? We can only confirm we sorted one element. You know, here in this previous example, we were saying, okay, well, everything on the left side and everything on the right side might not necessarily be sorted, but at least it's closer, right, to where it should be. In this case, we haven't really done anything. We basically split into these 2 arrays. So then we need to split the 4 array. So we're going to pivot on 2, then we're going to with 3, 4, 5. We need to split the 3 array. We're going to pivot on 3. We're going to get 4, 5. We're going to split the 4 array, get 5. Then we're going to have a 1 and 1, and then it's going to take that. So look, so the same example, right, took how many steps? 1, 2, 3, 4 iterations of the algorithm to run, and the one where we use 3 as the pivot only took 2 iterations to run, basically. So that's the worst case of n squared. And I do want to be a little more specific. I said where the list is already sorted, that is true, but it would also be a worst case if it was like backwards. I had to remember how to count backwards with 5 for a second, sorry. But it's because of the same reason, because you know, if you have 5, well, before the problem was that when we sort everything less than 1, there's nothing less than 1 and everything's greater than 1. Now we have kind of the inverse problem that we sort everything's less than 5, but nothing's greater than 5. So we're still only placing one element at a time. So in other words, the worst case for quicksort is when your pivot is always like the maximum or minimum element in your array. So that's some examples of that. I wrote a bunch of stuff here, but some conceptual questions we can talk about quickly. So let's say you have the worst case time, you have your already sorted or backwards sorted list. What can you do to improve that runtime? If anyone has an answer, please just tell.
Check your list first.
Sorry, what do you say?
Check it first.
That is actually true. That's not what I'm going for, but that is totally true. Shuffle is another thing. Yeah, so you mean just like, because in insertion sort, right? That's what we do. We basically scan through until we find an error, and if we find no errors, we're done. So this is a kind of broader conceptual thing, but actually, you're right that if you wanted to just check everything and see if everything's in place and then do it, that would work. Do you know what that would do to the best case and worst case? It would actually change them. Would it make the algorithm any worse if we did this linear check first?
Oh, but your best would be theta of n.
Yeah, your best would actually become n, because in the best case you just check everything, and then you're done. It doesn't necessarily make the algorithm better because you're probably almost never going to actually encounter this n case, but it is an interesting like algorithm design. If you want to artificially inflate your or deflate, I guess, your best case to make it look better on paper, you could actually do that. Anyway, that was a bit of a digression, but yeah, just the other things we could do are related to pivot selection, right? The problem here is that the pivot we're selecting is either the maximum or minimum unsorted element every time. So if we shuffle the list, if we just randomize it first, that will take linear time because all we do is just make some random swaps. And then we're much more likely, we're not guaranteed, but we're much more likely to have a good pivot at the start, right? Like probabilistically, if you look at this list, there are more things that are not the maximum or minimum element than there are that are the maximum or minimum element. Maybe that was confusing, but the point is we will probably get something better. And another thing you could do is you could have like a really intelligent pivot selection. You could just calculate the mean because you can find a mean in linear time, right? You just keep track of everything and see what's the mean. And then you can just select that as your pivot. And since that only takes linear time, it doesn't actually affect the asymptotic runtime of your algorithm. So those are some things you can do. Any questions on quicksort before we move to broader sort summaries? It appears no. Okay, so we'll move on. So here we're kind of summing up everything we did. So part A is basically figuring out, just denoting the complexity and of every sorting algorithm we know and the stability. So I will say that we already figured out quicksort. We just did that. So the time complexity of that is n log n in the best case, and it is n squared in the worst case. Do people know what stability is? Are people good with that concept? No. Okay. Great. Don't worry. Yeah, I never know what's, yeah, anyway. So stability is actually like, I think a relatively straightforward concept. It's just that if you have equal elements in your list, they stay in the order they appeared when you sort it. So let's say you have a list of, 1, 2, 3, 3, 4, or something like this. Notice there are 2 3s in this list. And just for the sake of distinguishing them, I'll call 1 3 and I'll call 1 3 prime, right? They're the same value. I just want to have a visual marker so you can distinguish them. So if you sort the list and you get this back, then it's stable because you keep, whoops, okay, yeah, it had to catch up with me. You keep the order of equal elements the same. But if you were to sort this list and maybe you end up with like 3 prime coming before 3, then it's not stable, right? So equal elements need to retain their original order in the list for it to be stable. We'll see why that's important in after we fill out this table, but does that concept make sense to people? Great. I'll give you just like a minute or two to fill out this table. This is a great thing to just, I guess you get like a cheat sheet. So to like write on your cheat sheet or just kind of memorize. This is very, very important. So I'll just give you a minute to look at it. How's it going? Do people know these? Okay. Does anyone want to hit me with the best case and worst case of selection sort? And I'll do stability afterwards. Right now, let's just look at the runtimes because that's kind of a different concept.
I think with selection sort, it was n squared for both.
Yep, it's n squared. Because remember what you do in selection sort, you basically scan, find the biggest element, pick it up, and then swap it at the end. And you do that n times. So it's always going to be n squared, right? Because you always have to traverse the entire array to make sure you found the biggest element. Okay, insertion sort.
N for best case.
Mm-hmm.
N squared.
It is n squared. Yep. Yep, because again, we first scan through, everything. If everything's good, we're done, which is that where we get that n. Otherwise, we basically swap until things are good. So the worst case there happens when you have like a completely backwards array, and you basically have to swap the second element once, and then the third element twice, and then the fourth element 3 times, etc., which is 1 plus 2 plus 3 plus 4, etc., up to n, which is an n squared runtime. Heap sort. How long does it take? Yeah, it does take n in the best case, which is just kind of a technicality of the array-based heap. If everything's equal, you can do it at n because you don't need to like bubble or anything really. And then the worst case is n log n, because you could imagine in the worst case, you pick the maximum element out of the heap, you swap it with the last thing, and then you gotta then take the last thing in the heap, put it at the front of the heap, and then bubble it down or sync it until it's in the right place, which is a log n operation, and we do it n times. Okay, and finally, merge sort.
Is it n log n for both?
It is n log n for both. Because what we're doing, right, is we're splitting things in half every time, which again is that kind of clue that it's a log algorithm. And then we're running this kind of linear combining algorithm within every iteration of it. Okay, some big questions, I guess, before we can do. So first of all, are any of these runtimes confusing to anyone? If anyone can't kind of figure out why they are the way they are. Okay, it appears no. And then the question I want to ask you is, we see that insertion sort here, right, has a best case of n and a worst case of n squared. And we see the quicksort has a best case of n log n and a worst case of n squared. So the best case of insertion sort's better than quicksort, and the worst case is the same. So why are we ever using quicksort, basically, right? Because it seems like we only have a higher bound or a better bound on the uppercase.
Is it because there's less cases where insertion sort's going to have a time complexity of n versus sort?
Yes, because so that's basically it. This is the important part to realize, that asymptotics are not everything. Constant factors in the real world matter. And the reality is the quicksort is the fastest of these sorts. You can tell because it's called quicksort. But yeah, so what we know is that insertion sort is going to only really get close to this when the array is nearly sorted. So if we're assuming a random array, which in the worst case we're going to, it's very unlikely we're going to get anywhere near this n runtime. But for quicksort, we're probably going to end up near this n log n a lot more often. And very rarely are we going to get this n. And even if we are getting close to this n squared, we just saw some strategies you could use to probably make it even better. So I hope that makes sense. Stability. The stability of these algorithms. Does anyone have ideas on these? Oh, someone, why not just use merge sort exclusively? You mean because it's always guaranteed to have the n log n, so why not, like, why risk the non-deterministic factors? Yeah, so the reason is because quicksort is going to run faster than merge sort still. I don't know about saying it's empirically better, but in the real world, if you just run on random samples, quicksort is going to outperform all these sorting algorithms on average. That being said, there are some things to do with stability for reasons that we do use merge sort a lot. Merge and quicksort are the most common ones of these. If you run like sort in Java on an array of objects, it will use merge sort, or it'll actually use like tim sort, which is a modification of merge sort. But it will use merge sort. So does anyone have any ideas on the stability of these? I don't know if anyone was able to figure these out. It seemed like a lot of people were confused on stability.
Insertion is stable.
It is stable, yes. Is merge also stable? Merge sort is also stable. We'll go over why all these things are in a minute, by the way. I'm just curious just to see what the intuitions are on people.
Heap sort is not stable.
Heap sort is not stable. That's kind of a meme. When you say like, what sorting algorithm are you? And you say, I'm heap sort because I'm unstable. It's kind of a meme. So that's how I remember it. But we'll explain why it is too. And the other two.
Selection, not stable.
Is not stable. That's correct. Can we go 5 for 5? What's the last one? If no one has an idea, that's fine, because it's totally fine. But quicksort is not stable. You can implement it in such a way that it might be, but in general, it is not stable. Okay, so now basically we're going to prove that each of these are stable. It says find an example, but if you can find an example where it isn't stable, that's proving that it's not stable, right? So the idea is we're going to take these and we're going to show that they're unstable. Does anyone have an idea of how to do this, or do you want like some structure of how to do this, or it's a vacuum cleaner outside my room. I hope it's not bothering anyone. Yeah, okay. So remember before I said basically, okay, let's take, an example like this, or something like this, where we have a 2 prime and a 2. Let's put 2 prime second because that makes more sense. You have 2 and you have 2 prime. If you end up with a sort like this, it's not stable because you've switched the order of elements that are the same. Similarly, if you had something that was like you had even more, where you had like a 2 prime and you had like a 2 prime prime 3, if you end up with any order where the 2s are not 2 prime 2 prime prime, it's not stable, right? That's just kind of the definition of stability. So yeah, if you end up with something, like this, it's not stable. So I'll give you a couple minutes to try to come up with some counterexamples for these 3, just kind of using your knowledge of how they work. And I would recommend trying to draw an example like this, where you have these kind of like prime elements and you see if you can create a situation in which they don't remain stable. I understand this seems to be a little bit of an out there concept to a lot of people. So I'll just give you until 11:50 and then we'll do some examples together. Okay, hello. Does anyone have any specific kind of small arrays that would demonstrate that these three sorts which are not stable are not stable? Does anyone have one for selection sort? Okay, so for selection sort, you're saying, oops, you said 34, 19, 20, 11, 11. 34, 19, 20, and let's say 11, and we'll say like 11 prime. Okay, so if in our sorted list, we end up in a situation where 11 prime comes before 11, it's not stable. So let's see what we're going to do with selection sort. So we're going to scan through, and we're going to find the biggest element, which is 34. And then we're going to swap the biggest element with the thing at the end, which means we're going to get 11 prime, 19, 20, 11, and 34. This is already looking pretty good because we've already basically messed up our order. Find the biggest element again. This case is 20, and we're going to swap it with 11. So 11 prime, 19, 11, 20, 34. We'll do it again. What's the biggest element now that we haven't sorted is 19. So we're going to do 11 prime, 11. It's going to swap with 19, 20, 34. And then neither of these elements are going to swap because they're the same. So yeah, that's an example that works. We see that these are no longer, that this is not stable. Great. Any examples with a heap that don't work?
Doesn't selection sort just move the rest of the elements in the array over one, like
Normal
context?
No. So the way that we normally do it is we swap, basically, right? So we find the maximum element and then we swap with whatever's at the end. Then we find the maximum of the remaining and swap with the remaining. And hopefully you can see that that is, a lot better, right? Because that's a constant operation, do that swap, as opposed to shifting everything over.
Right. So I guess that's the distinction between like the conceptual version and the much more easily, creatable, like the practical application.
Yeah. So this is how you would probably implement it. But yeah, I agree with you that you might do it the other way. But yeah, this is how the worksheet tells me to do it. But yeah, I thought of that way first too. But yeah, any heap sort examples? Let's just do a simple one. Let's just do a heap where everything is equal. So let's say we put 2 in, and we have a 2 prime, and we have a 2 prime prime. So we'll just say it's a 3 element heap, right? So first thing we're going to do is we're going to heapify this, and it's already done being heapified because, right, this is a max heap, and all the elements are equal. So there's no need to change, right? So now what are we going to do? We're going to take out the front element of the heap, which is just this 2, and we're going to swap it with the end element, right? So we end up with this 2 prime prime. 2 prime is not changed, and 2 gets fed to the back. And then we sync 2 prime prime. It doesn't change anything because these elements are equal. And we know that this part is sorted, right? Now we do the next thing. We take 2 prime prime out because it's the front element. We swap it with the what is now the end of the heap, which is just 2 prime. So we end up with 2 prime, 2 prime prime, 2. These things are sorted. We sync down 2 prime, but it just stays where it is because there's only one element in our heap. So then we just kind of pluck it out and put it right back in where it is to sort it. So we end up with 2 prime, 2 prime prime, 2, all sorted. And this is not right, or this is not stable, right? Okay, and then the final one is quicksort with Hoare partitioning. Does anyone have any idea how, oh, sorry, why is it not stable? Yeah, sorry, before I move on. Right, so an algorithm or a sorting algorithm is stable if the relative order of equal elements is preserved, right? So I've called these 2 prime, 2 prime prime, just so we can distinguish them, but they all have a value of 2. So you would never, sort one over the other. And so what we see here is we end up with a different order, and we end up with 2 prime, 2 prime prime, and 2, right? And because it's a different order, it doesn't work. I hope that makes sense. Yeah. Does anyone have an idea of how to do with quicksort?
For quicksort, the example above that we did was not stable, right? Because we swapped 18 with 18.
Let me see. Maybe you're right. That's super big braining the worksheet. Oh yeah, I remember. Yeah, sorry. When we swapped, yeah. It totally was. I think I may have erased the part where I did that, but you're totally right. It actually was a demonstration. So, or this one, yeah, this example. Yeah, because at the end, if you remember, we swapped these two. So you're right. Very big brain there. Good job. I'm going to write a smaller example just for the sake of demonstration. But yeah, so let's say we had like 3, 5, 2, we have a 5 prime, and we have a 1. So what we're going to do is we're going to select our pivot, which is 3. We're going to have our L and our G. We're going to say L. L does not like 5 because it's too big. G does not like 1 because it's too small. So we're going to swap them. So we get 5 here and 1 here and 2 and 5 prime. And honestly, I can stop right here because we're already in trouble because we've already put 5 prime before 5, which cannot happen. So immediately we have trouble. I hope that makes sense. And this is another great thing to like prove to yourself too, if you can come up with an example. Some broader conceptual questions. Why is insertion sort stable? Obviously, you can't come up with one of these examples because it isn't, but like, why is it stable? Say we have 2 elements. We have a 3 and we have a 3 prime, and we have, a bunch of elements in between that are, something.
Isn't it because it's only doing swaps with the element right next to it? So when you get to the comparison of prime, it's not going to swap.
Yeah, it's not just that it's doing right next to it, but yeah, it's only, it is done in cases. So yeah, it's only swapping with the element next to it, so you're right, and it's never going to swap with an element that's equal to it, right? Because once it's equal, we stop swapping. So, let's say that these, for example, are really big numbers. These x2 and x3 are like 10 and 20 or something. We're going to do a swap here. We're going to do a swap here. And then we're going to compare 3 prime to 3. And 3 prime is not greater than 3, or is not less than 3, rather. So we're not going to swap it. Yeah, so we're never going to do that. So that's a reason it isn't. And then the logic for merge sort is pretty similar too, in that we're never going to do these big sweeping swaps across the entire array. Notice that selection sort, we pick something out of the array and we dump it in a completely different part of the array. Same thing with heap sort in the way that bubbling works, or sinking and swimming works. Same thing with quick sort. We're swapping from completely different parts, irregardless of what's in the middle, or irregardless isn't a word or something. They say don't use it, whatever. But the fact that we're doing everything kind of explicitly next to each other in these cases, in merge sort and insertion sort, ensures that they're stable. Okay, apparently irregardless on the SAT. I don't really care about. I think it's stupid when people try to say things aren't words, because if you use them, it's a word. Anyway, so I hope that those things kind of make sense, and I'm going through this worksheet really, really slowly, but whatever. Yeah, so if anyone wants to say, what are some trade-offs we consider designing or choosing a sorting algorithm? Aside from just straight up runtime, because that's kind of the obvious one. Does anyone know anything? Why would we choose one over another? What did people say? Sorry. Memory usage is definitely important. Yeah, so memory usage, and that's related to recursive depth. So we don't really talk about memory complexity in this class, but in the same way that you say, oh, this takes linear time to run, it also may take linear time to store it. If you store one array, it would take linear time. If you imagine, for example, the kind of naive recursive quicksort, right, where you're breaking things up in half every time, look at all these arrays we're creating. There's like a ton of memory there that if you have infinite memory, it doesn't really matter. But if you're sorting something really, really big, you might not want to have that extra memory factor. So in this case, insertion sort, maybe it's slower, but insertion sort is done entirely in the original array, right? All we need to do is keep track of some like variables. There's nothing much there. And this is related to this idea of recursive depth, that yeah, recursive functions tend to be more memory intensive because you have to worry about like frames and stuff. And then someone said space complexity. Someone said, are they all ordered? Do they have a certain structure? That's definitely true, right? If you know your data is structured in a certain way, you might want to choose someone. So, let's imagine that, you have a record of like names and they're all handwritten, sorted alphabetically, and you want to sort the record of names. The person who sorted them by hand probably got most of them right, but maybe they only got a few of them right. So that's maybe a situation where you would get relatively few swaps. And in that case, quicksort might be good. Another thing is if you know that all your structures are really small, like you're only sorting like a size 5 array, just use insertion sort because the overhead of like quicksort isn't worth it in that case. Yeah, so those are some reasons why you would do that. It's also noon, so you can go if you want to, but I'm going to keep going because I always do. Okay, here's a much more interesting question, I think. And it's okay if you don't know why, because this is like, out of the scope of the class and everything. But why would we ever use selection sort, right? Earlier I said, why would we use quicksort over insertion sort? But the reality is that quicksort runs faster than insertion sort normally. Selection sort, though, always runs on the order of n squared, right? So why would we ever use selection sort over any of these others? It seems like there's no way we could improve anything. And someone said if the arrays are already sorted or nearly sorted, that doesn't actually matter with insertion sort, because remember, insertion sort, we scan through the entire array, find the biggest thing, put it at the end, scan through, find the biggest thing, put it at the end. So it doesn't matter if it's sorted already. The actual structure within, right, the way that the data is presented does not affect the runtime, if that makes sense. The same thing with merge sort in that case too. Okay, big money question, but I'll just explain it. So why would we ever use in selection sort? It has terrible runtime and never gets any better. One thing that you can notice though about selection sort is how it uses swaps. So there are two kind of operations we're doing in these comparison-based sorts. We are either looking at something or we're swapping something, right? We look or we swap. And we've treated both those operations as taking the same amount of time, for example, right? Because intuitively, they kind of probably do, right? You just kind of assume this is like a single discrete operation. You can do it at the same time. However, one thing you'll notice about, for example, insertion sort is if you look at the number of swaps in insertion sort, what you do, right, is you find the first thing out of place, then you swap it all the way back a bunch of times, and you keep doing that. So if you look at the number of swaps, for example, in insertion sort, it's n squared swaps in the worst case, right? But if you look at the swaps in selection sort, how often do you actually swap in selection sort? Well, you find something, which is a bunch of look operations, and then you only swap it once you found the biggest thing, right? And so you only do one swap per element, meaning it only takes n swaps. And so what this means is if you have a situation where, for example, looking at an element is very, very expensive for some reason, but swapping that element is not, it actually might be to your benefit to do selection sort, because selection sort is the only one of these sorts that only swaps like n elements. All the others swap way more, because in heap sort, you have to do all the sync ups and sync downs, which gives you like n log n swaps. For example, in quicksort, you have to do a bunch of swaps. In merge sort, you have to do a bunch of swaps. Does that make sense? Why you might want to do that?
Yeah.
Okay, super weird random application. And the reality is, for the most part, if you're doing a project and you sort something, you just use like whatever is in the libraries. But that's some like kind of more analytical insight into how you might do things differently. Yeah, and then our final question about comparison-based sorting. I'll just let you read it, and if anyone has an answer for me, please tell me. Basically, are there any sorts that run better than n log n in the worst case? Does anyone want to posit just a yes or no?
No.
Okay, people are saying no. Does anyone think yes?
Is it like on average or like?
It does say in the worst case. It is the worst case, so it's not. Okay, and you can tell that I'm trying to trick you because I asked if people say yes, because it is actually yes. Because this sort here, radix sorts actually run in worst case linear, which we'll talk about in a minute. But however, comparison-based sortings, which is probably the kind of intuitive sorts that we've done, most of the sorts we've done so far, selection sort, insertion, heap sort, merge sort, quick sort, all these, yeah, take it at least n log n in the worst case. But if you use a different kind of sorting technique, like radix sorting, you can do it in a better case. You can do it actually in linear, worst case. So speaking of linear sorts, we have radix sorts. Do people know how radix sorts work? Okay. Someone said yes. Oh, it's today's lecture topic, really? Okay. Well, we'll give you a preview then. So there are two main types of well, there are three main types of radix sorts, but we're going to talk about two of them here. This one is LSD radix sort, not to be used with, lysergic acid, dimethyl or whatever. It's least significant digit sort. Oh yeah, people can go if they want. It's getting pretty late. And then we have MSD, which is most significant digit. So in LSD, basically, we're just going to sort by least significant digit each time. So first round, we're going to sort by the ones place. Second round, we're going to sort by the twos place. Third round, we're going to sort by the threes place, etc. And just because we're like way over budget and it seems like people haven't done this, I'll just do this example and you can, follow along with what's going on, if that's okay. So we're going to sort everything by the ones place first, right? So if we look at the ones place, which one of these has the smallest ones place? It's 30392 has the smallest ones place because it's 2, right? Then the next biggest one, we see there are 2 with the with 5 as the ones place. So we're just gonna like pick those in order. So first we're gonna do this one, then we're gonna do this one, 30395, and then 30315. We're just scanning left to right. And then finally we're gonna pick this one because it's the biggest one, which is 30326. If that makes sense, right? And then the next thing we're going to do is we're going to scan by the ones place, or sorry, the tens place. So now we see that this like 15 is the lowest one, 30315. And then the next lowest one place is the 2, so 30326. And then we have 2 with 9, so we're going to just add them in left to right. 30392, 30395. Notice at this point, even though we're sorting by the tens place, really we're sorting by the hundreds place, because everything, the relative order is preserved here from our first iteration. And then the final thing is we're going to sort by the hundredths place, so we get 315. Actually, notice that they're all just the same, so we're not actually going to really change anything here. They're all the same. The next iteration is sorting, whoops, by the thousands place, but again, they're all the same. And then the 10,000 place, but they're all the same. Okay, and so now we can see these are sorted, right? And so the big insight into this that I want to give is that the reason these are sorted is because of stability. This is a stable sort, I'll just spoil, it's like a later question, but it's because of stability. And let me basically explain why stability is important. I forgot to do that earlier. What stability lets us really do, that's really cool, because it seems really trivial in the examples we did before, but what stability really lets us do is it allows us to apply multiple sorts at once. So for example, let's say you had like a spreadsheet and you had like students in it, and I'll just say like a student is named, X1, and you give them a favorite color, right? And their favorite color is, green, and you have their age, and it's like 3 or something like this, right? You have these two factors, right? So you can imagine we can sort them by age, and we can sort them by favorite color, and maybe we can even sort them by name too, but I'm not going to worry about that, right? If that makes sense. So what if we wanted to sort them both by the same thing? So let's say we sort them all with a stable sort. Let's say we sort them all by age, and then we sort them all by color alphabetically. What we're going to end up with is something that's going to look like this. What's the first alphabetical color? Say like blue. And we'll say this person's 3. And we'll say that's red. So notice basically that we sorted them by color alphabetically, but notice that within each color, all of these are sorted, right? The ages are sorted. And that's what you can do with a stable sort. So if we stably sort by first age, it will sort them all by age, and then when we sort by color, it will sort them all by color, but the relative ordering of everything within that color will also remain sorted, if that makes sense. That's maybe a little weird, but you can do this in like Google Sheets if you want. You can just sort things by multiple terms and it will actually stably sort them like this. This is a really important fact. I hope this kind of makes sense. Doesn't make sense.
Yeah.
Okay, good. Point is we can sort by multiple parameters and subparameters, and that's exactly what we're doing in an LSD sort, right? We're sorting all by the ones place first, and then we're going to sort by the tens place, and we know that once we sort by the tens place, that in every kind of 10 bucket, the relative ones place is going to remain sorted, right? So we know that here, where we both have 9s, we know that we're going to get 2 first and we're going to get 5 first because we're holding over that sort, basically. And then similarly, in the next place, we know that it's stable. We know that when we've sorted by the ones place, everything, or by the tens place, everything's going to remain in order when we sort by the hundreds place and successfully. So that's kind of the technique that LSD sort uses to stably sort things. That's the big takeaway. I hope that makes some sense. MSD is very similar. I'm just going to go over it pretty quickly because we're over and I see people are leaving. But MST is most significant digit, so we're just going to sort by the most significant digit instead of the least significant digit. But there's a little ramification here that we can't rely on the same kind of stability constant. So what we do is we sort things into buckets, basically. So these first couple sorts are the same because you see the first 3 numbers of all these numbers are the same. But once we are sorting by the 4th digit, we sort basically as you would expect. We sort by 30315. We sort by 30392. Oh, not 92, sorry, there's a 26 first. 30326, 30395, because we're just sorting left to right, and 30392. And we put them all into their own boxes, right? And then when we successively sort, we sort only within the box. So the last thing we're going to sort in this case is the ones place. But we're not going to sort all the ones at the same time. We're going to sort only the ones in this box, only the ones in this box, and only the ones in this box, right? And those boxes are determined by the previous sorts, right? I hope that makes some sense. So you can see that here, we don't have anything to sort. We don't have anything to sort because we only have one element, but here we do. So we're going to sort by most significant digit. The 2 comes first. Because the 2 is different than the 5, we're going to put it in its own box now. And then we have 30395 over here. And if there was another digit, we would keep going like this. I don't think this is a very good example of MSD because so many of the numbers are the same. But that's how it works in like a quick nutshell. Any questions on that? Okay, the answer is no. Similarly, the runtimes of these. So these runtimes are linear, I basically said already. But do we know what the factors are? Because the factors are a little different, right? We have W, which is the size of every word, right? Or the number of digits in every letter, right? Notice that we had to run this 5 times in both MSD and LSD because they're length 5 strings. And the number of actual elements. And then we have R, which is our radix, which is basically our base. In this case, it's a radix of 10 because it's base 10. But you could also do this in a radix of base 2 or something like that. Does anyone have ideas on how these would work? I'm just going to say them because these are kind of weird. But basically, it is W times N plus R, best and worst. And this one is just N plus R. And this one is also WN plus R. Sometimes you'll see this referred to as just like theta B, where B is like the amount of data inside of the like set of things. This is a little more specific. But basically the idea is we have to do this W times. We have to do it the length of the word times. So that multiplies the factor of how much work it actually takes per node, which is N plus R. So that's our radix and the number of things we actually have to sort. In LSD, it's always the same because we do it always the same way. But in MSD, we have this kind of bucketing strategy. And so basically, the reason that MSD has a faster best case is if you have different digits, basically, for the start of every first element, it's already over. So imagine, for example, if you have the numbers, 1,000, 3,000, 2,000, 6,000. If you sort these all by their first digit, 1, 2, 3, 6, right? It doesn't matter what the rest of these are, what the rest of these 3 digits are. It's already sorted. So that's where this best case is coming from, basically. And then the stability of these, both of these are stable. In particular, LSD really, really relies on that stability to even work in the first place. Radix is also stable. It just doesn't rely on it in the same way when you're actually doing the algorithm. I hope that makes sense. And then this is the final question, this is the last question. Is radix sort always the best to use? We see that these are linear factors, right? The best and the worst case are linear compared to our other sorting algorithms, which always have more than a linear worst case. So is it always the best thing to use?
I'm guessing no, or else the go-to wouldn't be quicksort and merge sort.
Yeah, if it was, if they were the best way to use, we would just always use them. But yeah, so some potential problems with this are, first of all, notice there are more variables here, right? This is not just like a simple n relationship. And so you could imagine if this W is really, really big, that's a problem, right? If you are trying to sort, maybe you're trying to sort only 3 words, but they're all like 10,000 digits long, and you're trying to do LSD, it's going to take a ton of time to sort each of those. Whereas with insertion sort, it would just be flip, 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 because you're just comparing things. So these factors can outpace the other factors. And the other thing to note is that, these are great because they're stable and everything, but you do have to have this fundamental property that like the thing is divisible by a radix in the first place, right? We're taking advantage specifically of the fact that we can think of this 5-digit number as a ones place, tens place, hundreds place, thousands place, 10,000s place. And you can't do that with everything you want to sort. If you want to sort, cats or something, it's not necessarily clear, that you could divide that into kind of radix-based subproblems and then sort that. You could sort cats by age, but then you're sorting by a number. You could sort cats by name, but then you're sorting by, just a string, which you could also do this because it's also easily divisible. But yeah, so that's the other big thing. You can't always describe something in terms of a radix, and if you can't do that, then you can't sort it in terms of a radix. Okay. Any questions about anything related to sorting? I'm not going to do the last part of this worksheet because I think it is so far out of scope that it's not even worth me like doodling around on it. Look at the solutions that they come out. They're super crazy. Any questions on anything?
No question.
Okay, all good then. Goodbye then. I think no, this is the last discussion actually, I think. So goodbye. I hope that the time has been good. Sorry, I've been gone for the past 3 weeks. That wasn't my fault. That was the election and Armistice Day and all those things getting in the way. But yes, goodbye everyone. I really enjoy teaching discussion. So good luck on the project. Good luck on the exam. Does anyone want to see my build your own world?
Sure, if you have it already. If you have it.
Yeah, 1 second, just because I'm going to leave this in the recording too, because it's funny. I've never done this project before, actually, because I took this class with Hillfinger. So this is the first time I'm actually doing this project. I thought it was pretty fun so far. I'm loading my IntelliJ, sorry. Oh, I can't show you my code. I was about to. I'd be like, that would be really bad if I just threw my code up in front of everyone, because, you got to do the project on your own. How do I run this? 1 second. Oh, here she is. Okay, hold on. Let me share my screen. Here's what my world looks like with like a random seed. I don't know that it's. I think I don't know if you're allowed to combine rooms. I did. I think some people said you weren't. I also have these, which I figured out how to solve these little points, but I haven't done them yet. But this is my world so far. So I hope yours is coming along well as well. But yeah, I will stop this recording.